All right, welcome back. So in this video, we'll be looking at harmonic functions this time. So this goes back to the uh, Cauchy-Riemann equations. So if we have a complex function, right, which is split up into real and imaginary components, um, the Cauchy-Riemann equations, say that partial of u with respect to x is equal to the partial of v with respect to y, and the partial of u with respect to y is equal to minus the partial of v with respect to x. Okay, those are the Cauchy-Riemann equations. All right. Um, so these here involve what are called partial derivatives, right? Partial derivatives, since we have functions u and v that are multi-valued, right? They are functions with respect to two independent variables, x and y. We can take a first order partial derivative. So first order here is just uses differentiating once, right? So you're differentiating u with respect to x once, right? This is a partial. You take the first derivative of v with respect to y once, right? This is the first derivative with respect to y for u, and this here is just the derivative of v, first derivative of v with respect to y, with respect to x, excuse me. So those are partial derivatives. And so there's also, we can take also a second, we can take second order partial derivatives. Partial derivatives. Okay, so they look like this. So this is a pure second partial derivative with respect to x, right? And we can take this here. This is the second partial derivative with respect to y. We can also have what are called mixed partials. So they look like this. Okay. Right. So regardless, these here would indicate the second derivative of a multi-valued function. Okay, x and y. So if we just look back at the Cauchy-Riemann equations, we can derive what is called we can derive what's called the Laplacian equation. So for example, if I were to take the partial with respect to x of the partial of u with respect to x, well, okay, this is just saying the derivative of the function partial of u with respect to x. So we differentiate that, and we can write this out as the second derivative of u with respect to x. Okay. All right. So, oops, let me actually. Actually label these wrong. So the pure looks like this with respect to y. Okay. Sorry about that. So this is indicating the second partial of u with respect to x. Okay. So and what that means is we just take the derivative of the partial of u with respect to x. Okay. So if I just switch these, so if I just put this over to the right and scoot this over a little bit and make this equals. Okay, so this is what the second partial of u with respect to x means, right? But by the Cauchy-Riemann equations, this equals to the partial with respect to x of the partial of v with respect to y. Okay? And so this would equal to the mixed partial of v with respect to x and then y. Okay? There's actually a theorem in partial derivatives. It's called Clairaut's theorem. And what this means essentially is that mixed partial derivatives are equal. Of a function are equal. So what this means is that the second partial of v with respect to y and then x, this is equivalent to saying the partial of v with respect to x first and then y. Okay. It's basically switch the letters around. All right. So that's what Clairaut's theorem is. And we can also rewrite this as the partial with respect to y of the partial of v with respect to x. With respect to x. And also by the Cauchy-Riemann equations, this equals to the partial with respect to y of minus the partial of u with respect to y. Okay. So all together, and so this would equal to this quantity right here. This would equal to minus the second partial of u with respect to y. Okay. And this is where we'll derive harmonic functions. Okay. So we conclude that the second partial of u with respect to x plus the second partial of u with respect to y is equal to 0. So this is a special name. So this equation here has a special name. It's what's called the Laplacian equation or Laplace's equation. Okay. And in other words, we can write out this equation like this. Del squared u is 0, where this del squared operator, it's equal to, by definition, this quantity. It's what it means, right? So right, that's the del squared. Okay, del squared. So del squared, this is by definition. So you're just distributing u, and that's just another way to write out this equation here in star by the star there. Okay, so this is a great condition to show second derivatives for multi-valued functions. Okay, so here is an important fact here. If a function u of x, y satisfies be Laplacian. It's also known as the Laplacian, so the Laplacian equation. Then the function u of xy is said to be harmonic. Okay. With a complex function is analytic. It means it satisfies the Cauchy-Riemann equations in some domain D. Then the functions u and v are harmonic. On the domain D. Okay. And also, since we have a function that is, so here's also another important thing to mention. If u of xy is harmonic, we can find a way to compute what is called the harmonic conjugate. And what that means is, so we just find a function v of xy that is harmonic and satisfy the Cauchy-Riemann equations. Okay, that's what's called a harmonic conjugate. So that's an important thing to take note here. So let's look at an example on showing a function is harmonic and figure out a harmonic conjugate. Okay, so show that log base e of x squared plus y squared is harmonic, and compute its harmonic conjugate. Okay, so I wrote out log base e like this. This will be apparent in the next video because we'll look at the complex logarithm. Okay, and that's going to be so the notation of the complex logarithm, it's going to be quite different. So when we look at this function log base e, we're going to typically associate with that with the natural log of a real number x, as you see, as you have seen in calculus. Okay, so we refer to log base e as your usual natural log of x you've seen in calculus. Okay, so so we're assuming that u of xy is log base e of x squared plus y squared. Okay, so first we need to compute the partial v with respect to x. Okay, so take the derivative of this function with respect to x and treat the y variables as constants. So that would be 2x divided by x squared plus y squared, x squared plus y squared. Okay, x squared plus y squared. Likewise, the partial of u with respect to y is should be the same, but with the y's. 2y divided by x squared plus y squared. Okay, next we need to compute the second derivative. Partial view with respect to x. Second partial view with respect to x. Okay, so we're going to differentiate this function here with respect to x and treat y as constants. So that would use the quotient rule. All right, here we go. So low times d high minus high times d low divided by x squared plus y squared squared. Okay, it's over that number. Second partial view with respect to y, it would be the same, almost the same. Y squared times 2 minus 2y times 2y over x squared plus y squared squared. Okay. And so that just happened. So second partial of u with respect to x, that would equal to so that would be 2y, hold on a second. Yeah, so it would be 2y squared minus 2x squared divided by x squared plus y squared squared. They'll have the same common denominator. That's a good thing. And the other one is 2x squared minus 2y squared. Okay? So since they have the same common denominator here, all we have to do is just look at the quantities in the numerator. So these quantities in the numerator. Okay? So all right, so we'll have x squared plus y squared squared, and then we'll have 2y squared minus 2x squared plus 2x squared minus 2y squared. That gives us 0. So our function is harmonic. So our function is harmonic. Next, we have to figure out its harmonic conjugate. So what we need to do is we need to find v of xy such that v satisfies the Cauchy-Riemann equations and v is harmonic. Okay? Well, just go off from the Cauchy-Riemann equations. Okay, so from the Cauchy-Riemann equations, we have here that the partial of u with respect to x should equal to this quantity here, right? And we also know that the partial of u with respect to y equals to this. Okay, so from the Cauchy-Riemann equations, we know that the partial of u with respect to x equals the partial of v with respect to y. And partial of u with respect to y is equal to minus partial of v with respect to x. Okay, so, or we can just say here, minus the partial of u with respect to y equals to partial of v with respect to x. Okay, so partial of u with respect to okay, let me write out. So the partial of v with respect to y, that means that quantity equals to 2x divided by x squared plus y squared. And the partial of v with respect to x, well, that would equal to minus 2y divided by x squared plus y squared. Okay? So that's what that means. Okay? So here's what we're going to do. We are going to look at this first set of equations, this first set of, or I should say the first equation of v, and to figure out what v of xy is, all we have to do is take the antiderivative of the function 2x divided by x squared plus y squared, and we're going to take the antiderivative with respect to y. Okay? All right. So to get back v of xy, we would have to take the antiderivative of this quantity with respect to y. Okay. So we're going to treat the x variables as constants. So this would equal to 2x times the integral of 1 divided by x squared plus y squared times dy. Okay. So what we will have here, so okay. So yeah, okay, I'll just start off with y. So really we can do a trig sub here to solve this integral, but this integral should equal to 2x times inverse tangent of y over x plus a constant. Now this constant would be a function in x, right? Keep in mind, we're integrating with respect to y. So what we can conclude is that a function v of xy looks something like this, right? Looks something like that form. All right. And the next step we want to do is we want to try to incorporate the second equation into this solution here, right? Into that equation on the bottom. So what we're going to do next here is we're going to take the derivative of v, excuse me, with respect to x this time. Okay, so this would equal to 2 times, well, we're going to have to use the product rule here. So I'll have an inverse tangent of y over x, excuse me, plus x times the derivative of inverse tangent of y over x. So that will use the chain rule. So we'll have 1, excuse me, 1 over 1 plus y over x squared times minus y over x squared. Okay. Plus w prime of x. All right. Hopefully that made sense so far. Okay. So this would equal to 2 times inverse tangent of y over x minus so okay. minus 2x times y over x squared over 1 plus y over x squared. Oops. Plus w prime of x. This is the partial v with respect to x here. Okay. And so, okay. All right. So, and we already know that the partial v with respect to x equals to this quantity, negative 2y over x squared plus y squared. So this equals to 2 times inverse tangent of y over x minus 2. So this is minus. So I have to be careful here. 2y over x over 1 plus y squared over x squared. Oh, I'm sorry, that's squared. Okay. So, and then plus w prime of x. Okay, we're almost there. Minus 2y over x squared plus y squared. If we simplify this equation, we'll have negative 2y over x squared plus y squared equals to 2 times inverse tangent of y over x minus. So, okay. I gotta make sure didn't make a mistake. Okay. So right, the x's cancel here. I'll get an extra x there. Okay. I had to make sure I had to double check to see what I did wrong. Okay, so so if I integrate this with respect to y, x tan theta. So if I do as u sub, right, back in Cal 2, oops, I need to do, or I should say, yeah, trig sub back in Calc 2, right? We can replace this integral in terms of theta. So this will be this substitution. Okay, so 2x is a constant and dy is that. So in terms of theta, this would equal to x times secant squared theta d theta over y is x tangent squared theta. So it'll happen x squared secant squared theta. And that, okay, so okay. So this equals to 2 times the theta. Okay, I see the problem. I see. Okay, so the x's cancel. So I have 2 theta. Theta is that guy. So 2 times inverse tangent of y over x. Okay. So this should be a 2 times inverse tangent. Okay, hold on. So okay. Mm, mm, mm. Okay, I gotta reflect off what I wrote down. Okay, so 2x. Um, it's secant squared. Um, mm, oh, I think, yeah, all right. So, okay, I'm doing it right. So, yeah, I had it wrong in my notes. So, yeah, the s's will cancel. Okay. All right. So, yeah, this is so let me erase this portion. Sorry about that. Like I always say, it doesn't hurt to double check. So, let me delete this. So, okay. So we're back to here. So really the function v of x, y should be 2 times inverse tangent of y over x plus some constant. So what that would be a function of x, okay? Then uh then from this point, we want to take the partial of v with respect to x. So that will simplify things a little bit nicer. So regardless, we're going to have to use the chain rule here. So this will be 2 times 1 over 1 plus y over x squared times so minus y over x squared. Okay, minus y over x squared plus w prime of x. Okay. And the partial of v with respect to x is equal to minus 2y times x squared plus y squared. And this equals to, if I do this right, hopefully, so this is 2 times minus y over x squared over x squared plus y squared over x squared plus w prime of x. Okay. And so we'll have minus 2y over x squared plus y squared equals 2. So these x squareds will cancel. Minus 2y over x squared plus y squared plus w prime of x. So hopefully that made sense. I had to check on the algebra again. So these are the same. So we'll have w prime of x equals to 0, right? And if the derivative is 0, that means the function w of x is just a constant. C is any constant. Okay? So therefore, the harmonic conjugate v of xy will be this 2 times inverse tangent of, in this case, y over x plus c. And this would be a function that would satisfy the Cauchy-Riemann equations. Okay? So, yeah, so hopefully that made sense. And that is pretty much it for this section. Sorry, it took pretty long. But here are some problems for you to check comprehension. So, 4, 8, 9. And for number 9, just show the harmonic conjugate for problems 4 and 8. Okay. Theoretically, you can do every problem in this book, but these are the suggested ones for you to do. Okay. So hopefully this is going well. In the next video, we're going to look at really crazy functions, starting off with the complex exponential and logarithm. So thank you for watching, and I will see you in the next video, huh?